Welcome to WikiPodcast.
Today, we're diving deep into a force that, well, shapes everything around us.
Gravity, yeah, from the simple act of an apple falling off a tree to planets circling the sun, it's all gravity.
And this is part of our physics series, looking right into the foundations of classical physics.
Our mission today is to really unpack how we got to understand gravity, mainly through Isaac Newton's eyes first, and then see how that picture, evolved.
And we'll uncover some pretty surprising connections along the way.
Okay, so before Newton, what was the thinking? Why did people think things fell down?
Well, way back, the ideas were very different. You had Aristotle, for instance. He didn't really think of a force pulling things.
Oh.
Yeah.
How did he explain it then?
He thought things just sought their natural place. Earthy stuff belonged on the ground, so rocks fell because they wanted to be there. It wasn't an interaction, more like an inherent tendency.
Huh. Sort of philosophical, but not really testable.
Exactly. The big change came later, with the scientific method taking shape. People like Galileo.
All right, Galileo was actually doing experiments, dropping things, rolling balls.
Meticulously measuring, yeah. He was challenging those old ideas by watching how things actually moved here on Earth.
And while Galileo's looking down, you've got Kepler looking up, using all that data from Tycho Brahe.
Mountains of data. And Kepler worked out his laws of planetary motion from that. Planets moving in ellipses, not perfect circles, speeds changing.
Revolutionary stuff. He described how they moved with amazing accuracy.
But crucially, not why. There was no explanation connecting the planet's dance to, say, dropping a rock here.
So we have these two separate pictures, Galileo for earthly falling, Kepler for celestial orbits, no connecting line.
Until Newton. And this is where it gets really profound.
His big insight.
He sees the apple fall, he sees the moon orbiting, and he thinks, wait a minute.
It's the same thing.
It's the same force. The force pulling the apple is the force keeping the moon circling Earth and the Earth circling the sun. It's universal.
Wow. That's the first great unification people talk about, isn't it? Taking gravity from just being an Earth thing to a cosmos thing.
Precisely. Combining earthly physics and astronomy. And he wasn't just speculating. He used inductive reasoning based on observations.
And laid it all out in the Principia in 1687.
His masterpiece, Philosophiae Naturalis Principia Mathematica. Yep.
Now, there was something about him linking Kepler's laws to the moon's orbit. Didn't he, run into a problem at first?
He did, yeah. He used Kepler's third law, the one relating orbital period and distance, to figure the force must weaken with the square of the distance, the inverse square idea.
Okay.
Then he tried to check if Earth's gravity, weakened over the distance to the moon, would explain the moon's actual acceleration. He assumed Earth's mass was all at the center. His first numbers were a bit off. The reason? The accepted value for Earth's size back then wasn't quite right.
So dodgy data nearly stopped him.
Almost. But luckily, by the 1680s, better measurements of Earth's diameter came along. Newton plugged those in.
And it worked.
Perfectly. The numbers matched the moon's motion. It confirmed the inverse square idea. And, importantly, he also proved mathematically that a spherical body, like Earth, acts gravitationally on things outside it, as if all its mass was at the very center.
That's huge. That makes the math manageable for planets.
Absolutely essential.
We should probably quickly mention Robert Hooke. He claimed Newton pinched the inverse square idea from him.
Yes. Hooke had sort of talked about an inverse square force, but, well, he didn't have the math, the proofs, the whole unified picture Newton built. Newton invented calculus, partly to solve these problems. So yeah, history generally sees Hooke's claim as less substantial.
Right. Okay, so let's get into the law itself. Newton's law of universal gravitation, what does it actually state?
Okay, the core idea is this. Every little bit of matter in the universe attracts every other little bit of matter.
Everything pulls on everything else.
Yep, and the strength of that pull, the force, depends on two things. First, it's proportional to the product of their masses. So more massive things pull harder.
Makes sense. And second,
it's inversely proportional to the square of the distance between their centers.
the inverse square part again. Double the distance, the force drops to 1/4. Triple it, it's 1/9. It falls off really quickly.
Exactly. Gets weak fast. The modern equation is F equals G times M1 times M2 divided by R squared.
F is the force, M1 and M2 are the masses, R is the distance, and G.
G is the gravitational constant. It's the conversion factor, the number you need to turn that proportionality into an exact equation with units like newtons.
Okay, G. Now here's a mind bender you mentioned earlier. Newton didn't actually know the value of G, did he?
He didn't. It's kind of amazing. His law was out in 1687, the first accurate measurement of G. That was Henry Cavendish in 1798.
1798, that's 111 years later, and Newton was long gone by then.
Correct. So Newton worked with ratios and proportions. He could calculate the relative forces, how much stronger gravity was here than at the moon, for example, but he couldn't plug in two masses and a distance and get the force in, say, newtons, because he didn't have G.
How did Cavendish measure it then? It must be tiny between normal objects.
He used a really sensitive setup called a torsion balance, basically measuring the tiny twist caused by the gravitational pull between lead spheres in his lab. It was incredibly delicate work.
Wow. So Newton builds this whole cosmic system without knowing that one fundamental number precisely? That's incredible.
It really is.
So Newton gives us this incredibly successful law, this force acting across empty space. But he wasn't entirely comfortable with that idea himself, was he? The action at a distance part.
Not at all. He found it deeply problematic philosophically. How could something pull on something else across a total vacuum with nothing connecting them?
Yeah, it does sound a bit weird when you think about it.
He even wrote that the idea was so great an absurdity that I believe no man who has in philosophic matters a competent faculty of thinking could ever fall into it.
Strong words. Calling his own discovery an absurdity. How do you deal with that?
Well, this leads to his famous statement, hypotheses non fingo, which means I feign no hypotheses, or I frame no hypotheses.
What do you mean by that?
He was basically saying, look, my math describes how gravity works. It predicts observations accurately. It's a good description of the phenomenon. But I'm not going to pretend I know the underlying cause or the mechanism. I don't know how this force transmits itself across space. He described the what, but left the why or how open.
That's a really important scientific stance. Describe what you can prove. Don't speculate beyond that.
Exactly, a hallmark of his approach.
Okay, so the law describes the force between point masses.
Yeah.
How does it work for actual objects, like planets or us, that have size?
Right, real objects aren't points. Technically, you have to think of each object as being made of zillions of tiny point-like bits.
Oh boy.
And you have to calculate the pull between every tiny bit in object 1 and every tiny bit in object 2, and then add all those forces up. Mathematically, that's integration.
It sounds complicated for anything not perfectly simple.
It can be, but here's another piece of Newton's genius, the shell theorem. He proved that if you have a perfectly spherical object,
Like a planet, roughly.
exactly, or a star, the total gravitational pull it exerts on anything outside is exactly the same as if you squished all its mass down into a single point right at its center.
So that's why we can treat the Earth and Sun like points when calculating orbits. It simplifies things massively.
Hugely simplifies things. It's a cornerstone of orbital mechanics.
Does the shell theorem say anything about gravity inside a sphere?
It does. Inside a uniform hollow shell, the net gravitational force is 0. Anywhere inside. The pulls from all sides cancel out.
Interesting.
And inside a uniform solid sphere, the gravity actually gets weaker as you go deeper, decreasing linearly towards the center where it's 0.
Okay, that makes sense. You have less mass below you, pulling you down.
Precisely. So building on this idea of gravity reaching across space, people developed the concept of a gravitational field. What's the idea there?
Think of it like this. Instead of just thinking about the force between object A and object B, you can say object A creates a disturbance or a field in the space around it, like an invisible influence.
Kind of, yeah. It's a vector field. At every single point in space, there's a little arrow, a vector, telling you the direction and strength of the gravitational pull per unit of mass if you were to put something there. It basically maps out the acceleration gravity would cause at any location.
So it's like a map of gravitational influence. You put a mass somewhere, and it just follows the direction and strength indicated by the field at that spot.
You got it. It's a really useful way to think, especially if you have, say, 3 or more bodies interacting. You just add up the fields they create.
And it's related to potential energy, too.
Yes, because gravity is a conservative force, the field can be derived from a scalar potential, gravitational potential energy. The work done moving against gravity only depends on the start and end points, not the path taken.
Okay, so Newton's law.
Yeah.
Elegant formula, inverse square, shell theorem, field concept. It explained so much, worked incredibly well for centuries, seems almost perfect for everyday stuff and even planets.
It is an astonishingly good approximation for most things we encounter. Why? Because generally, speeds are much lower than the speed of light and gravitational fields aren't super intense. The gravitational potential energy is tiny compared to the mass energy of objects.
But it's not the complete story.
Yeah.
There were cracks, Right, things they couldn't quite explain.
Yes, especially when extreme precision was needed or in very strong gravity.
Like, what were the clues that Newton wasn't the final word?
Well, the most famous early one was the orbit of Mercury. Astronomers observed that its elliptical orbit slowly rotates, precesses, over time.
Okay.
Newton's law, even accounting for the poles of all the other planets, predicted most of that precession, but not all. There was this tiny, persistent discrepancy left over about 43 arcseconds per century. It doesn't sound like much, but it was measurable and unexplained.
43 arc seconds. Persistent little anomaly. What else?
Light. Does gravity bend light? Newton's theory, if you treat light as particles with mass, which is tricky, predicts some bending as light passes a massive object like the sun. But observations during solar eclipses showed light bends twice as much as the Newtonian prediction.
Twice as much. Another puzzle.
And then, looking way out at galaxies, when astronomers measured how fast stars orbit the centers of spiral galaxies, they found stars way out at the edges were moving much, much faster than they should be, based on the gravity from all the visible stars and gas predicted by Newton's law.
Too fast for the amount of stuff we can see.
Way too fast. To make Newton's law work, you either have to modify gravity over large distances, or you need a lot more mass that we can't see.
Which leads to the idea of
Dark matter. This invisible stuff that has gravity but doesn't seem to interact with light. The galaxy rotation curves are a prime piece of evidence for it.
So Mercury's orbit, light bending, galaxy rotation. These were problems piling up for Newton's picture.
Exactly. They were signposts pointing towards a need for a deeper, more comprehensive theory of gravity.
Enter Albert Einstein and general relativity.
Right. Around 1915, Einstein offered a completely different way to think about gravity. It wasn't just a refinement of Newton's law, it was a total paradigm shift.
How so? What's the core idea of general relativity?
Instead of gravity being a force pulling objects across space, GR says gravity is the curvature of space-time itself.
Whoa. Okay, unpack that.
Think of space-time, the three dimensions of space plus time, as a sort of fabric. Mass and energy warp this fabric. Like putting a bowling ball on a stretched rubber sheet, it creates a dip.
Okay, I can picture that.
Now, if you roll a smaller ball nearby, it doesn't get pulled by the bowling ball directly. It just follows the curve and the rubber sheet created by the bowling ball.
So planets aren't being pulled by the sun's force. They're just following the curves in space-time caused by the sun's mass.
That's the essence of it. Objects follow the straightest possible paths, called geodesics, through this curved space-time. What we perceive as the force of gravity is just motion along these curves.
So gravity isn't really a force in Einstein's view?
From the perspective of someone freely falling, no. They're following an inertial path in curved space-time. It feels like a force to us standing on Earth because the ground is preventing us from following our natural geodesic path. It becomes a kind of fictitious force in that sense, like the force pushing you back in an accelerating car.
And this new picture, it explained those anomalies.
Beautifully. General relativity correctly predicted the missing 43 arcseconds of Mercury's precession. It predicted exactly the amount of light bending observed. It provides a framework consistent with these observations where Newton's law fell short.
Amazing.
Yeah.
But even GR isn't necessarily the absolute final word, right? There are still challenges.
Oh, definitely. For instance, the classic n-body problem, trying to predict exactly how three or more objects will move under their mutual gravity, still doesn't have a general, neat analytical solution. We rely heavily on computer simulations for things like star clusters or galactic dynamics. It's complex.
And people are still testing gravity, pushing the boundaries.
Absolutely. Scientists are always looking for tiny deviations, maybe at very small scales, using things like neutron interferometry or in extreme cosmic environments, wondering if GR itself needs modification, perhaps to reconcile it with quantum mechanics. That's a huge open question.
So what a journey. From Aristotle's natural place idea
Through Galileo's experiments, Kepler's laws describing the heavens,
to Newton's revolutionary unification. Gravity as a universal force, described by that elegant inverse square law, which worked amazingly well for so long.
even though Newton himself was troubled by the action at a distance concept.
And then Einstein comes along and reframes the whole thing. Gravity isn't a force, it's the shape of space-time itself, curved by mass and energy.
A picture that explains the subtleties Newton's law couldn't handle.
Yet, Newton's law is still incredibly useful, right? A fantastic approximation for almost everything we do, from launching satellites to understanding tides.
Absolutely indispensable in its domain. But for the deepest understanding, for extreme situations, for ultimate precision, we need Einstein's view of curved spacetime. It's a fantastic story of how our understanding deepens over time.
A true deep dive into the fabric of reality.
Couldn't have said it better myself.
Thanks for listening. Write us your opinion in the comments on Seishua. Considering Newton's vision of gravity as a force and Einstein's view of it as curved spacetime, which explanation feels more intuitive or surprising to you? Subscribe to the channel to help more listeners reach our episodes. Thank you and have an amazing day.